Hi, folks. This session is about Apache Pinot and how you can use them as AI agents. I do have a little bit of a cold, so I may go on mute to cough or get another cough drops or something. But so far, so good. Right, so I'm gonna share screen. Okay, what you're seeing here is a Jupyter notebook running inside VS Code. So I'm just going to present it this way because I have to run some code. So I want to be able to present and run the code at the same time. Over here, I have two connections. This is a connection to StarTree Cloud, which is a free forever Apache Pinot instance. It's a scaled down multi-tenant, but yeah, this is talking to Apache Pinot. I also have a Postgres database here that I'm going to start off with. Okay. So what we're going to cover here is just the basics on vector search, RAG, and ultimately agents, AI agents in real time. I'm Hubert Dulay. I'm developer advocate at StarTree. I've written a couple books. Let's get started. So what's a vector? Some of you that have come to this before may have seen this before, so I'm just going to kind of skim over this a little bit. So vector is just an array of numbers. And you can create an array. For example, I have two sentences here, ID S1, S2, and I'm just tallying instances of the words inside the sentence. This is basically a vector. You can do similarity search between them. Like for instance, they both have I and I have love as well. So they're somewhat similar, right? So what is an embedding? An embedding is also a vector, but the dimension. So if you think of these as a dimension, so there's four dimensions in this vector here. Embeddings are like thousands, maybe four, even more dimensions. And when they are created, they're not created by tallying terms in a sentence. They're created using a neural network machine learning model. What we did up here is called the bag of words. And if you were to try to get the distance between a sentence that's had the word good and not good, these would be very similar to one another. But the neural network or the embedding model can actually get the semantics of the statement and relate these two as not similar. Okay. What is a vector index? Well, a vector index is basically like a database index that allows you to look up things really quickly in a database. A vector index is just a index that allows you to look up vectors really quickly in a database. And a vector database encapsulates all that logic, all that information inside the database. So we're going to actually do this starting off with PG vector. PG vector is an extension to Postgres that allows you to do vector similarity. I'm just going to run that. And what we're going to do here is use this model called the sentence transformer. And this is a multimodal model. What that means is that this is the model I'm going to use to create embeddings out of my unstructured data. Unstructured data could be images, videos, and like natural language text, for instance, like the ones we showed above. And what multimodal models do is be able to take something like an image and text and put them in the same vector space so that you could do similarities. And I'll show you what that means here. So I'm going to set up the database. I'm going to load the database up with some images. This is how you create the vector. So if you look up vector, PG vector, you can clone it from a repository. This is open, and it'll automatically install it into your local instance of Postgres, right? And this is how you enable it. Create extension, and I'm creating a table called images, and I'm inserting images into the file. Notice right this line right here. I'm using that same model, this clip model, to convert it to an embedding, and I'm inserting that embedding into the table inside Postgres. Okay. And now let's ask for some images. I happen to know that we have some Van Gogh images of paintings. I'm just going to run that. Notice here that I'm using that same model to create an embedding out of this text. So that's what makes it multimodal. That model is creating embeddings out of those images as well as this text. And then I'm going to select from the table this this percent %s is my string. This embedding here is my image. Right here is the index. I'm putting it in the where statement, and I'm printing out what it found in the database. Okay, these are pictures of Van Gogh paintings, and these are the distance. So if when I did a distance calculation between this text and the image embedding, this is the result. So it is 10.44, etc., distance away from the text. Okay. There are some other distance algorithms you can run in PG vector. This is what we use is Euclidean, which is just the triangulation, the distance between, you're just finding the hypotenuse here between A and B. There's the inner product. There's the cosine. Cosine is just basically this angle here. How bigger or small the angle is depends on how far it is. The Manhattan algorithm or distance algorithm is just the same thing as the Euclidean, but you're assuming there are obstacles in the way. If you think of like if you're in Manhattan, if you're in any 2 points in Manhattan, you typically have to go around a building. So that's what this means. There are obstacles. Okay, so yeah, that's the basics of your vector similarity search. Here we're going to talk about how we will use that in a RAG use case. So again, we're going to take some, in this case, not images, but just any documents like websites or document page. We're going to chunk it, like break it up into pieces, because we can't create an entire embedding out of the entire corpus of documents. We're going to chunk them and then create embeddings out of them. So there's two ways you could do this. You could take the entire data set and just insert it into the vector database. Or if you're doing it real time, for instance, you're listening to document changes or anything that's changing, event fires, it gets chunked, it gets converted into an embedding. It could be streamed and then upserted into a vector database. So this is what makes it real time. You're always listening for changes in the corpus or in your unstructured data, and then updating the vector database so that when you do a retrieval from it or you do a similarity search from it, it's always new and correct and as of now. So in the retrieval in RAG, what you're doing is that you're submitting a query, and that query goes to the same embedding model, and you're pulling that information out of the vector database. So in this case, we're going to pull out text, not images. So that's what this context is. We're grabbing similar content inside the vector database, and then we're going to put the query and the context together and create a prompt. And this prompt is sent to the LLM to give a response. What this does is that the LLM will only respond if it has context around the information. So if this didn't return anything, if there's nothing similar in the vector database, the LLM will respond, I don't know anything about this this context, right? In Apache Pinot, we have a vector index as well. Let's say, for instance, we got a video, we're capturing frames. We convert these frames into embeddings. We have an embedding stream, and we write to Kafka, and then we load data into those embeddings into Pinot. Then we can implement search against that same table. And this is how the vector index in Apache Pinot is implemented. It uses a HNSW or hierarchical navigable small worlds vector. I'm not going to go through this because it's pretty complex. I read through it once and studied it a little bit. It was not straightforward. So I'm not even sure that I know completely understand it, but this is a visualization of what it works, how it works. Basically, layers, and there are graphs on these layers. And what makes it fast is that it's able to go down these layers and return um, similar vectors in the result. Okay. So we're going to go over two types of vector databases. The first, we did one with Postgres, which is an OLTP database. But and then we're going to do one with the Pinot, which is a OLAP vector database. When do you need to use which? Well, in an OLAP database, if your AI application needs millisecond latency for exact and similarities retrieval, or you have many concurrent users using your RAG application, or if you need a lot of historical data that you need to provide to the end user. So these are reasons why you would want to use an OLAP. Otherwise, an OLTP database could be fine for you. If you need consistency, this is a good thing to use. But most likely, you're going to use an OLAP vector database because of the amount of data you're going to be holding. Let's take, for example, New York City cameras. In New York City, there are over 50,000 street cameras in all 5 boroughs. And if each camera captures a frame every 10 seconds, that's about 157 billion records, embeddings in the database. This is a use case for obviously an OLAP vector database like Apache Pinot. You probably don't want to hold that much data in an OLTP database. Okay. So let's go, let me do a quick select here. This is the contents of that Postgres table. This is just a generic ID. This is the path of the image, and this is the embedding. Notice this isn't something that you would want to type out on a SQL editor or anything. These are very application based, and yeah, so this is not something typically this stuff you're going to use behind an application. All right. So now I'm going to introduce you to the Pinot vector index. We're going to use that, but we're going to use it instead of a RAG, we're going to use agents. So over here are my tables in Apache Pinot, a clickstream table, a product table, a purchase, and user. These are tables that are typically associated with like a clickstream or funnel analysis, right? So let me run this. So all I'm doing is selecting from clickstream. Let me show you a preview of this table. So it has event type, and this event type has things like all the values that you see in here. Clicks, views, saves, and purchases, right? This is, and if you could, render this to be able to drill down or, give you more specific information, but it's very, rigid, and there's a scope that you can't go beyond when using dashboards like this, right? By building agents, you can actually interact with these analytics a lot more than a typical real-time dashboard. So what agents are basically follow this path here. When you provide a query in like a RAG application, an agent takes it up. That agent is responsible for completing a task. And to complete that task, it uses tools. And it uses those tools to give you a response to your questions, okay? So we're going to try to build upon this dashboard of click streams, and maybe we can ask it more questions, right? So this here is just my connection to Postgres. This is my embedding information in the model that I'm going to use to embed. This is the number of dimensions I'm going to use. And then these are the tools. They're just Python functions. So this function here gets all the users of the application. Here gets the user's detail information, like it passes a user ID. Gets the recent purchases for a particular user. Gets a similar products based on a product description. Returns the top 3 users in the application based on, it looks like, purchases. And then who spent the most time on the application? Duration, limit 3. Okay, so these are just tools to be able to complete the agent's task. And the agent's task is this: you are a sales agent that's looking to get more users, to spend more time in an application, ultimately provide incentives, et cetera, right?
Are
Up
the
here,
notebooks on GitHub, or is there a link for those notebooks?
not yet. So I'm still working on this, and I'll make it available for you guys to download and use locally.
Thank you.
Sure. I forgot one thing here. Those same tools that I showed you above up here, I'm just providing more metadata. The metadata, more specifically, is the description. This description is going to get used by the LLM so that it can determine which functions or which tools to use when answering these questions, right? So now we have an agent. I've given this agent a bunch of tools. This is the LLM I'm going to use to help me just determine which tools to use to answer whatever questions related to this. Verbose is true, so it's going to print out what it's doing while it's going through this. And again, that's prompt that assigns the task or describes the task this agent is supposed to use. So I don't think I ran any of these. So let me run these. Okay. Done. Okay. So now we can start to ask it questions. Remember, this is going to use the same tables that populated the funnel analysis dashboard at the top. Right? So if I run this, it'll ask me the question at the top here. Who are the top users? Notice this is going to call functions, and it said, give me the top 3. It gave you the top 3. Who spent the most time? These are most time. And then it says, hey, these are your top users. Here are your top purchasers. Just their IDs, their time spent. Would you like to get more details about these users? Yes. So it's kind of like iffy, this thing running in the Jupyter Notebook. But notice that it's getting user details for each one of these, and then eventually spit out the response, right? So you can actually provide it even more. Yeah, there's your, would you like to reach out to these people? So it has an address. So let's say I'll do a similarity. So what product should I recommend to the top user? Oops. What product should I recommend to the top user? So it's got recent purchases for a particular user. And this is the product right here. This is mock data, so it's got a really terrible description to it. So it looks like it might be a book. It's like OpenAI might be taking a bit longer today, but it'll give you a response saying this user is probably going to be enjoy this novel here, and then even have it print you an email or a letter to send to that person, and so on. So I mean, understand that we've gone well beyond this typical rigid dashboard that gives you click down and drill up numbers. I actually want to execute a task. Imagine the other things you could do. That this agent just provides you a way to be able to interact with your customers. You can create other agents. You can have multi-agent systems that where the LLM will decide which agent is the best to be able to do the task that you're asking for. So imagine being able to, let's say, for instance, you're a CEO and each division of your company is provided with a KPI. You can actually ask a question: what is the status of the company based on these KPIs? And they might be able to direct you to a certain issue, or even identify one issue that might be happening right now. It's a great way to be able to expand upon the dashboards that you're providing. Um, but if you think about it, these things aren't, you have to build the agents. So they're all what these do you call them agentic applications. And if you have multiple users running these types of questions, you may want to be able to use something like an OLAP, like Apache Pinot, to be able to serve all these users, right? But that's it. Any questions on? So it looks like it completed. It says Stephen Bell recently purchased high quality titled recommend a product called Avoid Novel, etc. Right. So it did two things, right? It got that person's recent purchases. It looks like there was and then it got you the similarity search, right? So it did two searches for you, found you the recent purchases. Actually, did you a bit more. Actually, I remembered based on what it had before who the top user is. Decided to use that user to get recent purchases. Then decided to get similar products, and now you have that similar product here. Right? You can even ask for. It even gives you more options. So if it were me, I would probably add more tools to be able to ask more questions. Imagine this. If I had notice it took kind of a long time it was calling each one of these functions. There may be a faster way of like getting all of this information instead of going back. Maybe there might be one query that I could create or one tool that I can create to get all of this information instead of like going back and forth over and over again over a list of users. No, there are ways to optimize this as long as you give good descriptions to these tools, and then these functions or these agents will work faster, right? So it's good to kind of identify what kind of questions you're going to ask, and kind of monitor the performance to see how many times it's going to the database to retrieve things, how fast these queries are executing, and and so on. All right. Um, if you want to try the StarTree Cloud, you could scan this here. It is free forever, so I'm going to use it forever. They're pretty neat. So you could hear my products. Notice I have embeddings for the products so that I could do similarity search. I'm doing recommendation, right, based on the previous purchases of the user. So I'm creating embeddings based on the previous description, and I'm looking through the descriptions. This is the description of the product. This is the embedding that corresponds to this description. Any questions on this?
Hi, Hubert.
Hey,
Great presentation. I love the idea of using agents
Yeah, cool.
that communicate with Pinot.
Mhm.
I did have a question. Earlier, you mentioned there are various distance functions.
Yeah.
Um, uh, when using vectors in Pinot, do you have an option to select the different distance functions? And if so, how would you
Yes.
evaluate the accuracy of the different functions to select the most appropriate for your use case?
That's good. That's a good question. So here's so actually it was product. The product the product table has embeddings in it because I want to perform um similarity or recommendation, right? So here's that column embedding. It's a float. Is that a single value field? No. So it's a float array, right? So that's where the embedding goes. If you look down here, there, here's the vector. You could specify the type of distance function that you're going to use. It's best, there's no easy way to determine which kind of function you want to use. You have to test them out. Some distance functions will give you better results versus others. There's no way to tell. I can tell you this that Euclidean distance suffer, and so is Manhattan distance. They do suffer from this thing called curse of dimensionality. But that's meaning like if you have a really high number of dimensions, these start to get less accurate. But we're only using like 2,000 or 4,000 dimensions. If you get to like the 10,000 dimensions, you may want to switch to a cosine distance. But these are fine. Again, I would test out uh, a result that you know it to be true. Like if you know that the similar product to this product is going to be this, what is the score when you return the distance? You could do this down here. Where did I do that? Here. So the vector. This is the index here. It's doing a similarity, cosine similarity between the product embedding and the product this parameter up here. This description. Right. But notice that I'm giving multiple other results of the distance, right? Um, and this will you shall have cosine L1 and L2. This might be a good way to do it, no, but the vector index is going to be cosine, but maybe these might return better results. You're looking for something like where's that one I had up here? We'll run this again. Ah, I gotta rerun the whole thing. Anyway, if you recall, when it spit out the Van Gogh images, it had the distance like 10 dot something, 44. What I think it was. The smaller it is, the closer, obviously, the two points in the vector are. So you want to make sure you want maybe make sure that you analyze the returns of these functions here to see how low they get, right? Um, some distance algorithms might be lower than the others. If you know that points are two vectors should be really close, and this cosine only gives you 10, and then L2 and L1 gives you even a lower number, maybe try these other ones to see if they are perform better as far as similarity search. Does that make sense?
Yeah, you're basically saying use known good
Yeah,
examples and compare the different rankings or distance
yeah,
outputs against those examples to see which one
right.
fits best.
Yeah, it's this stuff is not um there's always got to be some kind of testing to especially distance algorithms to figure out which one's the best. Cosine is usually it's pretty popular because there's not really a use case that I can think of where it fails, but the others there are situations where they might fail. Any other questions? Great. Let me stop share. When I'm doing a similar version of this presentation at current, but so after that, I'll commit it and I'll provide the link to Yarden and to share with you guys. All right. Thanks a lot, you guys.
Thank you, Hubert. Thank you to everyone who joined, and we meet you on Slack, where I will share those resources with you. For any question, we're here. Hubert is here. I'm volunteering him. No, I'm kidding. And thank you. I wish you a great day or evening, and see you in the next meetup. Bye-bye.
Bye-bye.